All right. So yeah, that means that this setting is perfect. This setting we can go on. So where were we last time? Last time we talked about running process and a bunch of processes getting ready to run. Our class didn't discriminate multiprocessor or multi-core processor. But I don't plan to say anything about multi-core processor or multi-core processor. It just means that basically we have virtually many queues for each processor. Okay, so it doesn't matter whether there are multi-processor or not. We can narrow down to the topic that we have only one processor, one core. Okay, everything will still be the same. Now, what I'm going to talk about next is a very important concept called context switching. Okay, so context switching, I mean, it is not difficult to know that there exists such a thing. There exists such a thing called context switching, and the context switching idea means I want to switch from one process to another. Okay, but the technical context inside is needs some understanding of running a program or running a process. Okay, now first of all, this page used to be every year. I stand in here showing this page for more than 10 minutes to explain this. Okay, so if you have any difficulty in understanding this, raise up your hand, ask questions. So what is this picture? This picture is a whole summary of how a scheduler will step in. Okay, what is the meaning of a scheduler will step in? So scheduler seems to be a thing that is hidden, right? Originally, you have a process, right? A process running on the CPU, and while it's running on the CPU, suddenly, I usually call it suddenly, processor is being interrupted, okay, by whom? Okay, maybe by your scheduler, right? Your scheduler is saying that, oh, I don't want to schedule this process anymore. I want to schedule another process. And another process, say, from A, maybe not A, in the PowerPoint we call it P1, maybe from P1 to P2. Okay? So in this example, I have a clock here. Okay, so what is a clock here? It is very related to the scheduling algorithm. My scheduling algorithm is like this. We have a timer. For each processor, from each process, I have a timer. Okay? Say I want to schedule you to run on the CPU for 1 millisecond. Okay? So after exactly 1 millisecond, you will receive time interrupt. Okay? You will receive time interrupt. And the time interrupt say that, yeah, your share has been used up, your time has come. You have to go to take a rest. Okay? Let other process to run. Okay? So there's one type of events that the scheduler will step in. The number one type. Okay? Scheduler stepping means that we will pick another process to run. So I don't know what is this algorithm of the scheduler. Maybe the scheduler is following this order, say 1, and then next guy is 2, next guy is 3, so on and so forth. Okay? So then we will have P2. We have P2. Now, what scheduler next is, it seems to be a living guy there. Yeah, there's a guy, oh, this is P1, you finish your job, okay, I pick P2. After I pick P2, P2 will continue to run. Okay, remember, continue to run as if the scheduler is hiding somewhere again. Okay, suddenly appear, and suddenly it's hiding. Okay, and then hiding in the background, waits for some other interrupt. Okay, usually it's waiting for a timer interrupt. Say every process will have a 1 millisecond to run, and say I have 4 processes here, 1, 2, 3, 4. All 4 guys have enjoyed 1 milliseconds of our time. Then we will do it again, 1, 2, 3, 4 again, 1, 2, 3, 4 again, 1, 2, 3, 4 again, to give you an illusion that every process will have a chance to run parallelly. This is an illusion. Okay? Now, I give you another way to interrupt. To let the scheduler to step in. The second case is call for I/O, input output. So what are the meanings of call for I/O? You call scanf, you call printf, you call fopen, you call fread, you call fwrite, or what kind of F you have? Yeah, some other kind of if related file I/O. Okay, then you will have another chance. What is the chance? The chance is the scheduler step in. So this is related to the design of a computer. Okay, so that's why I said that this page will require many times to explain. Okay, I hope that I can add some transcript there so that people reading this recording is like, wow, how come it's so boring? Okay, so another thing is here, when I need I/O, say I have a 1 millisecond, I only take up 0.1 millisecond. I have 0.9 left. Okay, so will I still take the CPU for the remaining 0.9 millisecond? No. Okay, usually it's like that. When you ask for I/O, you leave the CPU. Leave the CPU means that yeah, I don't know why you still have a floppy drive. Okay, you ask the floppy drive to give you something. Of course, more than 1 millisecond. Okay, so while you're waiting, you shouldn't take the CPU. So the interrupt means have two meanings. I mean the interrupt is not two meanings. I mean you are waiting for something. So there's two meanings. One, you wait, then you shouldn't run. Second meaning is scheduler step in again. Understand what I mean? Because you don't need the CPU service. Okay? You're waiting for something. CPU was just idle. I don't want CPU to be idle. So CPU will execute the code for scheduler. Scheduler will pick another guy. Say the another guy is called P3. Okay? These three guys, P1, P2, P3, are ready processes. So I will pick P3 now. And P3 so happened that this P3 is a stupid program. Okay? It is an int main void and then return 0. Okay? Yeah, you can have a program like that, right? And then return 0. So it will immediately die. Yeah, it will immediately die or die with a very short duration of life. Now what happened is another chance for the scheduler to step in. Okay? So this, I mean, that's why I said that you have to be very conscious about the design of a computer. Yeah, one is there's a clock there. A clock will generate interrupt. Two, we have I/O. You wait for I/O. Third, we may have a chance that a process just died without using up to 1 millisecond. So what will happen? Again, scheduler will step in. Okay, scheduler will take the chance here. Oh, you don't want anything, right? Because you call a system call and you jump into the kernel, so the kernel knows that you don't want anything. Okay? You don't want anything, so scheduler should take this chance to pick another job. It so happened that, I don't know why, there's a magic. The data that is required by P2 just comes, okay, within this time period while P3 is running, okay, just magic. So what will happen, maybe we will give P2 the chance to go on. Okay, it's just a matter of a scheduler. Okay, the scheduler wants P3 then P2. Maybe the scheduler wants P1 then P1. Okay, so this small diagram already, I would say, explore all the possibilities. Nearly all the possibilities. We have I/Os. We have we call this a voluntary lapse. Voluntary lapse the CPU. Involuntary. It's still voluntary. Means your code don't know that you don't want CPU, right? Okay. And here voluntary again, except here I will come back. You will execute the code. Okay. So this is 10 minutes. Not 10 minutes. Any question you want to ask? Usually with this slides, people will start stun here. What you're talking about? Suddenly, there's so many ingredients act together. Okay. Any problem? So that means that while a process is running, you have many ways to live. Yeah.
Is the clock has any relation between the alarm system clock?
Your question is that the alarm system clock and this clock, whether they're related. No. I mean, you can treat it as the same hardware clock, but it's not set by the alarm system clock. So it is a kind of automatic heartbeats. Okay. So the heartbeat comes, and I will see that whether your time has come. No, you go on. And when heartbeats come again, oh, your time is used up. Go away. Okay. So it is I will say that the same hardware clock, but in terms of software context, they're different. Any other questions? Any other questions? No? Now then remember this figure. This figure will be hiding in all the slides beyond this page. Okay, suddenly I will say that, oh, context switching comes. Okay, why context switching comes? Maybe one of the reasons happens. Okay, some process die, some process waits for I/O, some process use up its own share. Okay. So what exactly will happen when process need to give up the CPU usage? Now it's become very easy to understand. Okay, it's just like playing a game. So they're using your maybe this outdated example, PSP. Okay, how many of you still have PSP? Now it's not PSP, PSV, right? Now it's PSV. Okay, so now remember, not remember. I mean, if you have the experience, when you play PSV, you want to play this game, and before you switch to another game, what you need to do is to save the game progress. Right? And you can choose not to save the game progress, up to you. Okay, but I will usually save the game progress and switch to another game. And switch back to the previous game, I need to save the later game's progress, and basically this cycle is go on all the way until I have run out of battery. Okay? So now what is going on here, I show you some examples or some details operations. What happens if I give up a CPU usage or forced to give up? Now here, say I will call a system call sleep. You know what is sleep, right? So there's a voluntary based give up of the CPU usage. Now I will switch from basically for state diagram, I will switch from a running stage to an interruptible state. I don't want to execute anymore because I'll call sleep. And you know, sleep is interruptible. I can press Ctrl C, I can stop sleeping. Okay, so I will say this interruptible sleep. And interruptible waits here have 3 steps to go. Okay, so what is this 1, 2, 3? Okay, we will explain it one by one. Okay, step 1. Step 1 is here. Okay, I will do some backup. So what is the meaning of do some backup? Okay, so inside the kernel space, you all know that there is a representation structure inside kernel space for that particular process. Okay, we call it a task structure, or a job structure, or process structure, whatever name you want to say. Okay, that structure not just storing the PID, not just storing the the list of open files, okay, or running time. Not just this, but something more. Okay, it will store. Yeah, what is this? What is this box? This box is your registers values. Registers values. So what does it mean of register values? I don't know how deep you understand in using a computer or writing assembly program. So basically, you doing computer operations. I don't know whether addition or not, or multiplication. You all work on CPU registers. Okay, not work on memory only. Okay, so while you are doing such a switch, okay, the CPU or the scheduler won't wait until you say you are in the middle of doing 1 plus 1. Okay, it don't care about what you are doing, either in the middle of 1 plus 1 or in the middle of formatting a disk. I don't know what it is, but I just want you to stop. Okay, then at this particular moment, I will back up this set of register, pull them out, and put it into a box. Okay, we call it a context, CPU context. Okay, and save it to the kernel space. Okay, we can do so. We can pull them out, put it in the kernel, and that's why every process will have this backup. Okay, every process will have this backup. Now, this is step number 1. And what happened to this code? This code we don't need to care. Okay, because this code usually is a read-only. It won't change. Okay, it doesn't matter if it's lost. Okay, maybe some process want this to swap out of the memory. No problem, we can call them back. There's a read-only. Now, some of the thing that is very volatile are CPU register values. So we have to save them, and while we are saving them, we are get ready to find another process. Okay? So when you find another process, we are basically saying that, oh, we find this white guy. This is like read white. White guy. Okay, this white guy previously should be running on the CPU, and that's why he has a previous save status. Okay, all the CPU register the status already there. Okay, there's a previously saved, and when I choose this guy to run, I will pull that box out and write it to the CPU registers. Okay, just like that, just like you're playing PSP or PSP. Okay, you load the save data and put it back to the game. Okay, and put it back to the CPU, and that means that I switch from one context, the old context, to new context, and continue to run. Okay? You may have a question saying, oh, how about the operations that done by the scheduler? Will the scheduler use registers value? Yes. Okay? So that means that when you really switch those CPU resources, switch those CPU registers, basically you are asking the scheduler to stop. Okay? So you ask the scheduler to stop, put all the things up, and immediately you will switch to this program. Okay, the entire process is switching from one context to another. We call it context switching. Any problem you want to ask? No? Yes?
What's the function of
Program context, where it is?
program counter?
A program counter, or what is program counter? Program counter is a very important CPU register. It points to the line of code that you are currently running. So that means that you replace the program counter. That means that you jump back to the line that you previously ran. Okay, and it is a CPU register. So that means I'm on the line 1, 2, 3, 4. So I back up. So I know that previously you're running line 1, 2, 3, 4. And when you resume, I put back 1, 2, 3, 4 there. Okay, so I know that you're currently re-execute or continue to execute a statement. Okay? Any other questions? Yes?
Where does the context of the process store?
Where does the context of the process store? It's stored in the kernel space.
But the arrow with number 1, you point to the user.
About the code, because it's for a program counter. Program counter say that, okay, I'm first running this blue guy, I don't know, green guy. The green guy is an old program. And while it's running, I want to switch to another program. So the program counter will point to the scheduler. The kernel space here. I don't want to run anymore. So the next will trigger the scheduler. Trigger the scheduler means that the program counter inside CPU now I want to run the code of scheduler. Then the scheduler choose this guy. Choose this guy. So at last I will put all the backup back to the CPU and switch to this program.
So can I say a process have at least 2 parts? One is program and another is context of a
Again here.
Can I say a process is consists of at least 2 parts? One is
2 parts. So
one is program
One
and
is program.
another is context of the process.
Not just that simple, also the memory, the user space memory.
The context of the process also.
Basically, why we first save the CPU register, because the kernel code also needs those registers to run. Kernel is just a piece of program, so it also needs registers. Okay, so before you can execute the things inside kernel, you have to back it up, or you will just override the previous jobs. Okay, so this is reason number 1. Reason number 4, of course, is to resume. Okay, we want to resume previous code. And back to your question is whether the context only contain the program and the CPU register. Process.
Yeah.
And what?
The process consists of a program and the
program.
context of the process.
And the context. Basically, you miss the memory.
But the context of the process also includes user space memory.
Context also contains user space memory. No. If I'm talking about the context here, I just talk about the CPU register.
Can you turn to the previous slide?
Yes? Previous slides?
The last.
Oh, right. The union of here. So I made a mistake. Okay. So I'm just thinking of you're talking about this context. Yeah. So that's why I said that we also need user space memory.
So
User space memory. Yeah.
Is it included in the context of the process?
I mean, I don't need to switch them. I don't need to switch. Just keep it there. Okay. Because we have tons of memories, right? We are more than enough memory. So just leave there, okay? You don't need to swap out. But for CPU register, they're just one set, okay? We cannot say that, I have I don't know, 1 gigabyte of register values. So I can just keep the old process there, okay, and let the scheduler to run, and then try to run the new process without swapping out. Yeah, I know what is your confusion. The confusion is, how about CPU address, right? How about a piece of memory stay in the CPU address? It's supposed to be there. So how come to say two processes have an address ABCD, okay? Address 1, 2, 3, and it contains the value 1 for one process. Another process contains value 2. Why not? We don't need to swap, right? In the virtual memory part, I will answer you. Okay, the virtual memory itself is, I cannot explain it now, basically. I will explain to you in the virtual memory part. Okay, any other questions? Yes? Process control block, not quite. Because the context control block is, what I said is, are you talking about assembly part of the context control block? Means, how can I explain? If you are talking about the task structure inside the kernel, I will say yes, because it's also contain this kind of thing. But when you talk about context control block, I don't know whether your concept of context control block is the same as mine. So can you explain a bit what is your explanation of a context control block? No. It's more than that. It's more than that. What you're talking about is user space memory as a whole, right? But I'm talking about it when you do the backup is done in the kernel space. So basically, you cannot say using pointer in your program. Try to get back the backup. It's not possible because it's hiding in the kernel space. Any problem? No? Okay. So this is what we call context switching, and why I need to say about context switching, because context switching is something that we don't want to happen. Yeah, we don't want. And the illustration, this is the worst case. Worst case. The worst case is if I need to swap a process of, swap means that I want to have a process 1 stop and execute process 2. And what happens if process 2 contains memory that inside a hard disk? Okay, so basically, under this case, if we are looking for performance, we are looking for performance. Basically, I don't want this process to run, the process G. I don't want him to run ever and never one, please. But yeah, because of awareness, the operating system, the user, want to drive this process. And when the process is driving, it's know that, oh, part of my memory or whole part of our process is already in the hard disk. We need to copy it back. So this is the worst case. And what are some other cases? There are some still other worst case, like you switch from one one CPU core to another CPU core. Okay? So I don't know whether you know about it or not. How many of you know that there is L1, L2, and L3 caches? Only a few. Okay? So when you are having one process running in a particular core, okay? So the cache will be in L1 cache. But suddenly you know that I will have a chance to switch from one core to another. Now, given that operations, basically I have to copy all the L1 cache from A core to B core. Okay? So that is another huge penalty to pay. Okay? So basically, in the elite class, I will talk about more how to keep a process within one core. Okay? Don't try to process, put this core and then go to another core. Okay? We don't want it to happen. Okay? But in here, we already can foresee that some of the context switching is unavoidable. We have to switch. Okay? And that's why, for a scheduler, usually we try to delay it. Okay, although I know for this, I need that guy to run. Okay, but can we delay it? or can we make a better schedule? Better schedule means that some jobs need to be executed first. Okay, like yeah, in your real life there are many these kind of jobs like your assignments, right? Some assignment have to do it first. I know some jobs is even more important, like playing the games. Okay, but you know, you have a priority, right? So maybe we finish all the high priority job first, or this kind of IO intensive job we will put it later. Okay, so later we will talk about this kind of operations, this kind of management. Okay, wow, I already told you that before. This is going to be boring. Okay, so any questions before I go on? No? All right. So some basics about process scheduling. Okay, really basics. Okay, nothing special. So first of all, processes, right? You already know what is a process. Process is basically following the orders inside the program and execute. But depends on the program itself. Okay, now this is not a process now. Depends on the program itself. We have different category of execution, right? Basically, we have two. One is called I/O bound here. One is called CPU bound. Okay. So what is I/O bound? What is CPU bound? Okay. CPU bound is a process that has such a definition. The user time is actually much greater. Okay, not just greater. It's much. Okay. User time bigger than system time. Okay. So what are the best example? Your data structure assignments. Yeah, all data structure assignments are CPU bound. Okay, think about it. You just read the file once. Usually it's once, not twice or many times. Okay, pull out the data, put it in the memory, and I don't know whether this is a die struct algorithm or bubble sort or other kinds of algorithms that you are going to run. You will all keep the CPU spinning as busy as possible. Then at last you print the outcome. Right? So that means the beginning and the end of the process will become I/O bound. And most of the time is CPU bound. Okay? So I will categorize this kind of a process. What happened? Is this running out of battery? Yes. Always me. Yeah. Always me. 哎呀。唔係我吹水㗎，你問下佢哋一次都係我㗎，次次都係。唉，喂，冇買。哦，OK OK，come back。Okay. So, well, first fortunately is that I'm not feeding the signal into the computer. Okay. Now, another type, what is that? Is system time greater than user time. So, what are they? LS, right? What is LS? LS is ask your hard disk, what is the directory content, and the hard disk gives you data, and what you're doing is just print it out once. Okay? So, getting it is I/O, printing is I/O. Right? So any other user time? Yes, maybe sorting the outcome. Right? Usually LS is a sorted outcome. So you have to sort the outcome. But in comparison, you will find that more I/O time will be needed. Okay? Or networking programs. Networking program is a perfect example for I/O bound. Most of the time you spend on waiting. Right? You wait for incoming data. Okay? And when you send it out, and like you just try to imagine what happened during BT. Yeah, think of it. What is the hottest part of your computer? Not the CPU, it's a hard disk. Then it's the network card, right? The network card just go crazy. I don't know whether you have tried it. Okay. Once upon a time I was not a kid. Okay, I was close to PhD graduation. I don't know why. Just by magic. Okay, I opened up the box. Okay, to let it have higher speed because the lower temperature, the higher speed the computer is. I don't know why. I just have my thumb put on the network card chips and nearly burn my finger while I'm doing high speed transfer. okay, not BT, okay, high-speed transfer. That network card chips is just like burning crazy, okay. And another thing is, right, the hard disk. While you're doing BT, e-donkey, I don't know what kind your email, right? What are the things you can imagine? You can see the hard disk lamp keep flashing, right? So that means all the things concerning IOs. So network programs, huh? And some others are hybrids, like a 3D modeling things, 3D games. So what are the hybrids? We have what? Compares. Compares need CPU to calculate the strategy, right? And what are the I/O bound process or I/O bound part? The part for I/O bound may be writing to the network or waiting from the network. Okay, your inputs, right? I don't know what kind of keyboards you are using, mechanical or not, I don't know. But still, this is I/O. Okay, no matter how fast you can type, this is I/O. Okay, plus this is the mix. This is the mix. Field-level rendering. You have heard of the rendering part containing a CPU computation, right? We have to calculate collision or something, but don't forget, you have to write it to the screen. Okay? You can write it to the screen or even get the model. The model is a hard code in the file. Right? You get the model from the file I/O and then do a process and write to the display card, the GPU. I don't know what is it. Okay? But this is a mix. So you will have a chance to have this kind of thing. Okay? So if we are going to study scheduler performance, okay, basically we have to select the good victims. Okay? So what are the good victims? Yeah, so let me do a very short summary first. Okay, the first summary is about, what is this? Okay, there's a 4 category here. Okay, the 4 category is the process scheduler, or scheduler here, is trigger. I don't know why it's going to scheduler. The process scheduler is trigger. Okay, so this is a small summary. When the trigger is, maybe you call fault. Right? You call fault is a perfect moment. I don't know whether the process parent or the process child will run first, but it is a perfect moment that we may have a chance to drive the scheduler. Say, my preference is always, I am OS, and the OS preference is always run child first. Then we need scheduler to step in, right? We need it. If we don't have a scheduler step in, how come we will switch from the parent to the child? This is perfect moment. Second, you want to terminate yourself. Third, wait for I/O. Okay. Fourth, finish wait for I/O. Usually after you finish wait for I/O, okay, the CPU will get interrupt. Okay, when you finish the interrupt, we will schedule the original process. Say, while P1 is running, okay, we tap keyboard. So the keyboard interrupt come in. So after handling the finishing the routine of the keyboard, so should I continue P1 or find another P, maybe Pn, to run? We don't know. So basically, this is another good chance, okay, for the process scheduler to step in, okay. Or one more thing, but I won't recommend you to try it. Okay, so what is that? You can do a search on Google or even look at the main page called Sketch U. So what is Sketch U? This is system call. This system call to tell the kernel that you don't want CPU. Yeah, you can keep on doing while one Sketch U. Yeah, basically, I expect the CPU usage will still high because you are doing while one, but you are doing while one for, very very interesting. I give up something indefinitely, and you need CPU resource to fire up this request. Okay, so basically this thing won't have a very low CPU usage, but you can try it. But I don't recommend it. This is nothing important. But just to let you know that there exists a system call to forget about the CPU. I don't want to give it up. Okay, so we have different classes of process. How about a summary? Any questions? Okay, before we go on, we have a summary. Any questions? Any questions? This is important. This is a recapture of previous diagram. No questions? Yeah, I know that it's boring, okay? So we have a scheduler classes. Okay, we have basically two classes, okay? I don't need special things to explain to you, okay? How to pronounce this is called preemptive. Non-preemptive scheduler. What is the meaning of non-preemptive scheduler? It's the time that while you're sleeping, no one can interrupt you, right? While you have a scheduling the job called sleeping, okay, in your real life, I mean, okay, no one can interrupt you until you find that your job has finished. You understand what I mean? Or you are doing a TV games, okay, playing games, okay? It is non-preemptive scheduler. While you're playing games, no one can interrupt you. No one can stop you from doing that until you find yourself finished doing that. Understand? So, what is that? It's basically a kind of scheduler. It's not a kind of process, first of all. It's a kind of scheduler. The scheduler will allow the process to take 100 CPU utilization until the end. No one can step in. No one can share the CPU until it give it up by himself. Just like what I just said. While you're sleeping, you will spend the whole time to sleep. Okay, you won't share. It's not possible that while you're sleeping, you're doing homework, right? Yeah, I usually have a dream like that. Okay. Yeah, while I'm sleeping, I finish the homework. When I wake up, oh. Okay, and while you're playing games, you cannot do your homework, right? Unless your homework is a called game. Okay, is there exist any kind of homework like that? I don't think so. Okay, this guy disagrees. Okay. Yeah, so that means it's you're very clear to you, right? Non-preemptive scheduling, and there is such kind of scheduler. Exists, really exists. Okay, but no more. So what are their properties, or where can you find them? You can only find them in mainframe computer back in 1960s. Okay, 1960. Oh, by the way, do you know who are the? First of all, there's two questions. So mainframe computers, where can you find it? So that means who will buy them? Second questions. When you buy them, why? Mainframe computers, huh? So, a mainframe computers, your slower smartphone nowadays is even faster than that. So basically, where can you find them? You will find it in two places: banks and universities. The university usually doing simulations. Okay, so this is one of the usage. And what is their requirement is to fit in program, right? Fit in a program, and what they want is a printout. Okay, it's a printout, just like what you're currently doing. But in a 1960, okay, this is solo purpose if it is in a university. And in the banks, even more crazy. You can imagine. They are being brought to do sorting. Yeah, they do sorting. Doing sorting. Yeah, very makes sense, right? You sort based on the balance of the account. Okay, the highest account balance, the guy is the VIP, right? The least one, you don't need to care about it, right? So at that time it's like this, but when it evolved, it become a database and even other kind of different services. Okay, and why there exists such kind of thing? Now, when you hear why they're there, so one is doing simulations, okay, doing computation, and another is doing sorting. The two guys, okay, these two guys, one is performance, right? I want the simulation to finish as quickly as possible, and I want the sorting to finish as quickly as possible. Don't care about the algorithm, okay? You have a perfect algorithm, but you can implement it wrong, okay? Wrong implementation. You can do it wrong, okay, or do it slow. I don't know why the algorithm is correct, but you code it in a slow way, okay? So basically, we ask for performance, good. So when we want performance, that's why I want a job to go to the CPU without going out, and then wait for your finish, and then you finish, I schedule this one. Okay, so as to minimize the finish time, okay, from the start to the end, I can minimize it. Okay, now how about, oh, by the way, the cons, okay, the pros and the cons. And the cons is, of course, this is not a type of computer scheduler that you will face nowadays, right? Think of it, okay, while you are doing BT, you can do other things. I don't know whether you love it or not, okay? Or your mom want to play a game, then you cannot do other things, okay? You cannot ask your mom to play games while you're doing BT. Yeah, it's not possible, okay? So nowadays, we cannot find any things like this anymore, okay? And today's we have another class of scheduler. It's a class of scheduler, not a class of process. It's called preemptive scheduling, okay? Preemptive scheduling is your nowadays, computer, cell phone, or whatever things you can imagine, okay? And why they will be preemptive, usually it's based on the previous understanding, the clock, the I/O, the termination, or the fork, okay? They will preempt it. Preempt means stop, okay? Stop or interrupt, okay? So that means that it's an interruptible scheduling or preemptive scheduling. Now again, where can you find it? Well, we usually find it in a system. Usually we call it timeshare system. Timeshare. Okay, you can already know what is timeshare system. Means a process go into the CPU for some time, and then you have to go out, and then other process go into for some time, and then you go out. Say I have 100 process, each process consume 1 millisecond, and you have an illusion that they run in parallel. Okay, and no matter how many cores, how many CPU you are having, basically you virtually have different queues, and that's all. Okay. And why they are invented, of course, you know, we have a high responsive system, right? Very responsive, so many processes do together. Okay, but the bad thing is the reverse of a non-preemptive scheduler. It is something that cannot reach the highest performance. Okay, say for example, you can imagine that you can write an assembly code, okay, without putting the OS, just do sorting. And of course, it's the fastest, right? You don't need to care about something happens, okay? Some Facebook message come in and interrupt your sorting, okay? So you don't need to care about this. But of course, this is not about today's computer. And let me finish this slide and we end this lecture. This slide is just talk about the goals of our scheduler, okay? Design goal. What is the design goal of scheduler? Now, first of all, fairness, right? You don't expect that my process is more important than yours, right? Or someone who launched an infinite fork has a higher performance or higher priority than yours. Okay, we don't want it, okay? But usually this fairness will collide with other parts of this triangles. So one of the things is policy enforcement. Okay, usually the root account, the administrator account, should have higher priority than yours. Now think about it. If you launch an infinite fork using the highest priority, can the root stop you? No. Okay, the root cannot stop you. Okay, so elite class guy, we will try to implement such kind of scheduler. Don't worry. Yeah, we will cause your scheduler go to a dice. Okay, and how about we reverse the process, okay? If you're doing infinite fork, you're an ordinary user, you are at a lower priority. And if I'm a root, okay, I launch some process will have a high absolute priority, absolutely high priority. I have the most important status. Then I will execute my job, the scheduler, will pick my job because I have a higher priority and my job is to queue all the infinite fork, okay? So this is bad or good, okay? In terms of a system administrator point of view, it is good, but in terms of you guys want to do some damage, it's bad, right? So one more is the balance between every part of the computer. So I want, while I'm doing CPU scheduling, it's great if I have a part in an I/O part, say the hard disk. The hard disk is spinning and getting data for you. While it's getting, I want to schedule another guy, okay? Which is perfect, okay? Can we have this? Yeah, basically in every scheduler nowadays, we have this design in the mind. Okay, these two are usually in the mind of a modern scheduler. This usually is I don't know which kind of scheduler you will find, maybe in some Department of Defense of the United States. Okay, their computer may have this kind of control. Okay, so this is the conflict diagram. Usually these two are good partners. Okay, they comes together. Usually this is the big brother. Big brother. Usually if you have this guy being enforced there, usually I want to have my process to win over some other guys. Then it means that it's unfair. As well as usually if you want to have an I/O, okay, maybe the big brother will also fight with you with the same I/O or fight with you with the same CPU resource. Okay? So when we come back next time, yeah, don't care about the figures. I find it very hard, okay? Yeah, basically these four figures are not related. Yeah. While I'm searching for it, okay, they are not related. Okay, so we will understand other kind of scheduling system. Not the scheduler itself, the system as a whole. Okay? And then we will understand what is a scheduling algorithm. So what is the algorithm input and what is the algorithm output, whether we consider online scheduler or offline scheduler. Okay? So next time, it's next week. Okay? So have a happy holiday and do whatever things you want. I will put up the videos as soon as possible. Okay?